Hey everybody, and welcome back. In this video, we're going to recap where we're at in the course and start to talk about good forecasting practices. In particular, the importance of making your forecast precise and capable of scrutiny. So this is a course on inductive logic, as we know, and all along we've been viewing logic as the study of proper inference, right? As a discipline distinguishes good inferences from bad ones. The inductive logician assesses the strength of an argument's inference in terms of its inductive strength. That is, how probable its premises render its conclusion. Now we set for ourselves back in week 1 the task of constructing a scientific inductive logic. That is, a formal system of inductive logic that would supply us with a more precise understanding of inductive probability and a method for determining the inductive probability of given arguments, making judgments that would align with common sense and with scientific practice. We saw in week 2 that rationally justifying the use of such a system of scientific inductive logic leads to thorny and rich philosophical problems, as pointed out by David Hume. We also saw that the construction of such a system is going to be challenging, given the failure of a simple proposed starting point, like rule S, in light of the group paradox. This led us then to consider Hume's proposal that we can't hope for rationally justified formal system of inductive logic, and we should just rely on our habit or instinct when it comes to judging the inductive strength of arguments. This last week, we explored various ways in which our instinctual judgments of inductive strength can go awry in systematic ways on account of things like the gambler's fallacy, base rate neglect, and so on. Right? This then provides some more pressure for us to move to the positive project of coming up with a scientific inductive logic that we can employ to correct for our own biases. Right? So not settling for just what Hume proposed, maybe it would go off of habit or instinct, but striving for that formal scientific inductive logic. This positive project is going to begin this first week by looking at some of Philip Tetlock's work on forecasting. By learning a little bit about good forecasting practices, we can hopefully gain some practical wisdom that we can employ in our class forecasting project and maybe even outside the class in forecasting. Then next week, we'll dive into probability theory, which will be our more formal scientific inductive logic. All right, so as I said, this week we're going to be looking at some of Philip Tetlock's work on forecasting. Now, Philip Tetlock is a political scientist at the University of Pennsylvania who's known for his work on forecasting. What is forecasting? Well, forecasting, as we explained in the video on the class forecasting project, consists in using historical data and trends to make estimates of the likelihood of various possible future events. Right, these could be political events, like who's going to win some election. It could be economic, like what's the unemployment rate going to be this summer. They could be climate related, like day-to-day weather forecasts or longer-term trends about global temperature. Really, we can make forecasts across a wide array of domains of human life. Now, we can think of forecasting in terms that are going to be familiar from this course as an attempt to assess the inductive probability of arguments that take this form, right? Arguments that move from our current stock of knowledge to some proposition that we're interested in forecasting. Maybe it's a proposition or a statement about how an election is going to turn out, or about what the employment rate is going to be at a particular time, right? So we can view what forecasters are trying to do is come up with inductive probabilities for these arguments. Now, Phil Tetlock, as we said, is a professor at University of Pennsylvania. His fame originally comes from work he did on expert political judgment, but more recently it comes from having started a group that's known as the Good Judgment Project, which was started as a part of a large study on human forecasting practices. So it was actually built, the Good Judgment Project was actually built to compete in a large-scale forecasting tournament, sort of like a much bigger version of the class project that we have for this course. So the Good Judgment Project was going to compete against other teams of forecasters, including some with U.S. intelligence officers on them, who had access to classified information, a lot of experience, right, so some advantages. This study went on for a span of about 5 years, from 2010 to 2015. They surveyed and forecasted on a wide array of different questions, different areas. And what Tetlock found was firstly that forecasting is difficult, right? Which is pretty much what he had found in his earlier work on political judgment, right? Humans are not always terribly good at making very accurate forecasts. In fact, sometimes our guesses are no better than random chance. You might have guessed that, right? Given all the cognitive biases that we covered last week that affect our ability to appropriately assess the inductive probability of arguments. But what was arguably more interesting was that Tetlock found that good forecasting is not entirely hopeless. Some of the forecasters with the Good Judgment Project actually performed remarkably better than chance, right? And these are the folks that Tetlock dubbed super forecasters and then wrote his book about. By examining their practices, we can hope to learn something about effective forecasting. So that's going to be our goal for this week. Right? But before looking more closely at some of their good forecasting practices in future videos, today we're going to look more closely at some of the difficulties that are involved in running a good forecasting tournament and assessing the quality of a forecaster's judgments. So let's start by thinking about an example that's taken from the Tetlock book involving an infamous prediction regarding Apple's uber successful iPhone. So Steve Ballmer, who's a billionaire former CEO of Microsoft, famously predicted back in 2007 that, quote, there's no chance that the iPhone is going to get any significant market share. No chance, right? And this prediction was widely pilloried in the media years later as Apple's iPhone product became the incredible business success story that we know it to be today, right? Probably many of the people watching this video have iPhones. So, right, this became a case of Steve Ballmer seeming to make a terrible prediction and being pilloried for it. But was Steve Ballmer really wrong, right? His prediction didn't come true, it seems, right? The iPhone was tremendously successful. But we have to be careful here, right? The prediction as stated is a bit vague, right? For example, right, what is, right, a significant market share, right? And what market are we talking about? The US market, the global market, cell phones in general, smartphones? At the time that Philip Tetlock wrote his book, iPhone controlled about 42% of the US smartphone market, right? Plausible on any precisification of significant market share, 43% is pretty significant. But iPhone only controlled 6% of the overall global cell phone market, right? If Steve Ballmer was referring to the global cell phone market, his prediction doesn't look quite as bad as if he were talking about the US smartphone market, right? So this highlights the importance of clearly defining the terms of the statements when we're trying to forecast. So, right, clearly defining what market we're talking about, what it means to have a significant share of that market, right? If we could get really clear on that, then we would be able to assess whether this was an accurate forecast or not. As it is, it's a little too vague, really, to say exactly how good of a forecast or bad of a forecast was, even though it really does seem like a bad forecast. We want it to be more precise. Another example of a notorious forecast that's also discussed in the Tetlock book involves the open letter that a group of economists and social commentators sent to Federal Reserve Chairman Ben Bernanke back in November 2010 after the major economic crisis. So they said this was a letter where they were urging the Fed to stop its quantitative easing program because they thought it would lead to inflation. They said, "We believe the Federal Reserve's large-scale asset purchase plan, so-called quantitative easing, should be reconsidered and discontinued. The planned asset purchases risk currency debasement and inflation." Right? So as it turns out, inflation never rose significantly following the publication of this letter, and the Fed's loose monetary policies have continued. Right? So does that mean that the authors were wrong? Well, you could possibly argue yes, because perhaps in the context of the letter, it was suggested that the authors expected inflation to happen within the next few years, but the letter doesn't actually specify a time frame, right? So it would still be possible for a signer of this letter to argue that the letter hasn't been proven wrong because inflation is still coming down the pike, right? This highlights the importance of having a time frame when you're making forecasts, right? We want to have a time frame included in our forecast for the sake of precision and accountability, right? The authors could also argue further that they weren't in error because they didn't directly predict inflation, right? They just predicted risk of inflation. And maybe there was a risk of inflation that just never materialized, right? So how do we tell if there was indeed a risk of inflation? Well, a fantastical, but albeit impossible way would be to roll back history and allow events to unfold repeatedly and see how often inflation occurs in this situation, right? Now suppose that contrary to fact, right, we could do that, right? Even so, there would be a problem here, right? Because suppose that we saw 10% of the time inflation resulted after this rollback process. Were the author's letters, were the letters of this author right to highlight serious risk of inflation in this case? Well, who knows, because they didn't quantify how much risk they thought there was of inflation, right? That is how likely they thought inflation was to occur. If they had given us a precise probability or percentage, we could work with that. But as is, right, it'd be too vague, right? Would the 10% count as having been a significant risk or not? Right? So the basic lesson here, right, is that if we're going to be effective forecasters and combat our own tendencies toward overconfidence and confirmation bias, which we looked at last week, it's important that we receive clear and unambiguous feedback from the world that can alert us to the accuracy or inaccuracy of our past predictions, so that then we can learn and adjust the way meteorologists do. That means that we need to make the statements we are forecasting very precise, right? They have to have a clear timetable and clearly defined terms, right? I tried to write all the questions on our forecasting project, the one for the class, so as to meet these criteria. Even if we make the statements we are forecasting very precise, though, there are still major issues with assessing the accuracy of a forecast, right? Life is full of uncertainty, and we often don't just want to predict that something's going to happen or not happen. We want to make a more fine-grained assessment of how likely it is to happen, right? But imprecision can creep in here too, as it did in the case of this open letter to Ben Bernanke, right? If we say things like, it's very likely that something's going to happen, or there's a significant risk that something's going to happen, that can be too imprecise to really assess the quality of those sorts of judgments, right? This, right, motivates us to come up with probability judgments or forecasts that are either precise probabilities or at least intervals of probabilities, right? So this connects up with Sherman Kent's so-called words of estimated probability, which were a way of making precise various sort of vague terms that we use in forecasts, like almost certain or probable or probably not, for the purposes of the intelligence community. So the U.S. intelligence community uses these terms to give, uses this key to give some precision to our normally vague terms, right? So, for example, right, certain, we say that means 100% probability. Almost certain, we say is 93% probability, given or take about 6%. So we're giving it there an interval, right? Interval from 87 to 99%. So we're giving it some more precision. Probable, 75%, give or take 12%. Chances about even, 50%, give or take 10%, and so on. Right? So this is helpful for the intelligence community because it makes clear what we mean by probable or probably not, right? When if we didn't have a key like this, we could have wildly different ideas about what these terms mean, and it'd be hard to assess the accuracy of a forecast, right? So how does giving precise probabilities help us to assess the accuracy or the quality of forecasting judgments if we can't actually do this historical rollback thing where we can roll back history and see how many times something would happen, right? If we could do that, right, if somebody estimated that the probability of an event was 0.6, right, and we could go back and we could repeat history, right, and see that event happens, right, 60% of the time, then we could say, oh, that person was accurate, right? They got it right. But seeing as we can't do that, how can we judge the quality of a set of forecasting judgments? Well, one way is through looking at the calibration of the judgments. So calibration is a notion that we've introduced in some previous videos. But we say that a set of probabilities or set of forecasting judgments are well calibrated just in case n% of the statements that are assigned a probability of n over 100 are true, right? So for example, right, I'd be well calibrated if 80% of the statements that I assign 0.8 probability to turn out to be true, right? And 90% of the statements that I assign probability 0.9 to turn out to be true, and so on, right? Calibration is a nice feature of a set of judgments, right? We can judge a set of judgments to be better if it's well calibrated. One reason for that is that being well calibrated makes you a sort of expert, right? Someone that someone would want to defer to about these forecasting questions, right? So if if you know that 80% of the judgments to which I assigned probability 0.8 turn out to be true, and you don't have any more information than me, and you then learn that I assigned 0.8 to a particular proposition, that would give you reason to assign yourself 0.8 to that proposition, right? Whereas if you learn that only 50% of the statements that I assign probably 0.8 to turn out to be true, then you actually wouldn't want to assign 0.8 to a proposition that you learn I assigned 0.8 to, right? So being well calibrated can help make you sort of expert. There's some nice graphical representations of calibration and the different errors we can make when it comes to calibration in the Tetlock book. So here we have these charts that look at along the x-axis. There's your forecast. This is the number that you assign to as your probability to a particular statement. And up here is the on the y-axis is the percentage of those statements that turn out to be true, right? So perfect calibration will be right along this straight line here, right? So, right, if I assign 0.5 to a statement, it turns out that 50% of those statements turn out to be true, right? If I assign 0.8 to a statement, 80% of those statements turn out to be true, right? So that's this straight line would be where you're perfectly calibrated. If you go over the line, then you're undercalibrated, right? Because then if I assign 0.2 to a statement, those turn out to be true much more of the time, 50% of the time, right? So I'm underconfident here, right? If my line is if I'm below the line of perfect calibration, then I tend to be overconfident, right? So if I assign 0.8 to a proposition, only 50% of those turn out to be true, right? I'm overconfident. So these are two errors that you could make. Now, calibration is good, right? It's a good feature of a set of probability judgments, but it's not all there is to making a good set of forecasts or a good set of probability judgments. Another feature we would like our probability judgments to have is resolution, right? So you could have somebody who assigns maybe 0.5 to all different propositions, and half of them end up being true, and then they turn out to be perfectly calibrated. But we're not going to say that there is in as good an epistemic situation as somebody who assigns 1 to all the propositions that end up being true and 0 to all the propositions that end up being false, right? That sort of omniscient person, right? That person, the second person, is more accurate than the first. We want to capture that, right? And resolution is the idea that captures that, right? A resolute assignment of probabilities involves more extreme probability estimates intuitively, right? So estimates that are closer to 0 or closer to 1. And what ideally you'd want to have would be forecasting judgments that would be both well-calibrated and resolute. So again, there are some graphs we can take from the Tetlock book that illustrate this fairly well. So we can see in the graph that's on the left side of the slide, we see an agent who is well-calibrated but not very resolute, right? So they only ever assign forecasts that are between 0.4 and 0.6, right? And indeed, the ones that they assign 0.4 to turn out to be true about 40% of the time. The ones they assign 0.6 to turn out to be true about 60% of the time. So they're well-calibrated, but they never, right, they're not good at identifying or separating out false propositions from true propositions, at least as well as this person on the right is, right, who is also perfectly calibrated, right? His forecasts fall along that line of perfect calibration. But, right, he assigns, right, high probability, 0.8 and above, to propositions that end up being true, and low probability, 0.2 and below, to propositions that end up being false, right? So that's this agent on the right is not only well calibrated, but they're resolute, and so we'd say they're in a better state or better forecaster than the one on the left. Okay? What we ultimately want when we're judging the quality of a set of forecasting judgments is going to be a measure that'll take into account both calibration and resolution, and that's what the Breyer score ultimately does, which we discussed in our video on the class forecasting project, and which we'll discuss again on Wednesday. Okay, so what are our takeaways from today? Right. Well, good forecasting questions are precise, right? Involving no vague terms or vague timelines, right? By being precise, they allow us to test for whether we've actually have been good predictors, good forecasters, and therefore keep ourselves accountable and learn and grow, right? Furthermore, good forecasts involve probability assignments that are well calibrated and resolute, right? And we'll ultimately measure that using the Breyer score. One other point I should make about good forecasting questions is that not only is it good that they be precise, but we also want them to be tractable and non-trivial, right? So there's certain propositions like, or certain questions like who's going to win the presidential election in 2036, right? That are just totally opaque to us, right? I mean, it wouldn't make sense to really try to spend a lot of time coming up with a good inductive probability for the argument that starts with our current stock of knowledge and goes to some conclusion about who's going to win the presidency of the United States in 2036. That's just, it's too opaque, too difficult of a question to forecast. There's other questions that are just too trivial for us to worry about forecasting. So like, if I drop my pen, I know it's going to fall, right? I know that that's supported by my current stock of knowledge. I wouldn't need to spend much time, forecasting that. There's other questions like who's going to win the presidential election this year, or how many coronavirus cases are we going to have in California by the end of May? Stuff like this. That's in this sort of sweet spot where they're important questions that are not trivial, not obvious, but tractable. We can do, or we can make some fairly decent estimates of inductive probabilities that start with our current stock of knowledge as premises and move to conclusions about what's going to happen in the case of those events. So when we're forecasting, we want to focus on those sorts of questions, right? Questions that are tractable and non-trivial. All right. So thanks for watching this video. Please remember to complete the participation poll. And don't forget that homework 3 is due tonight at midnight. And we'll continue with with more on good forecasting practices on Wednesday. All right. Thanks, guys.